Okay, so the game we're going to be recreating today from scratch is one of my favorite mini games of all time. It's from the Sonic the Hedgehog series. It is the Sphere minigame. So the first of three problems that we had to tackle while trying to recreate this game came in the form of the level structure itself. So we wanted to have the ability to load in and save different levels, and we had to think about how we could represent our grid inside of a raw file format. So if you think about any one spot on the grid, it has four possible states, right? There can be an empty spot that you're standing on, there can be a red ball there, a blue ball there, or a ring. So since we only need four states for every spot on the grid, we can actually split a byte of data right in half to represent two cells, and that's what we ended up doing. And this allowed us to save space in the final level size, and we didn't have to use any compression. So it was a good system that we ended up with. And that really tackled the first problem, but then we had to move on to how we're going to design the actual grid. The levels in the Sphere minigame are known for being what I like to call infinity levels. So if you go out the top with your character, you actually come in the bottom, and it's all seamless, so you never actually see this happen. Same if you go out left side, come in the right. So my first thought when doing this was to use ghost copies of the level for all of the borders, right? So you can see in this diagram, our main board would be number 5, and anytime we hit the top of number 5, we would change our coordinates to the bottom, and this would all be seamless for the user. If I was in the top left, I would see the bottom right corner of number 1, and this system worked fine. It's just that rendering this many copies, 9 copies of your level, made it perform very poorly, and it just wasn't going to work for larger levels. So we had to come up with a different solution, which became the viewport algorithm. And it's kind of simple to understand. If you look here, we are the orange dot, the player is the orange dot, and half of our viewport is formed by that red barrier there, and the other half is formed by the red barrier in the bottom right of our grid. And these two sections come together to form our viewport. And you'd think this algorithm of stitching different parts of your level together would be slower, but it is actually much faster. So that tackled the grid design problem and gave us infinity levels. But there was one more key aspect to the Sphere minigame that we had to tackle, and that was the rolling horizon. These games have a sort of fake 3D effect applied to them after the fact. And I believe in the original game, all they did was used a series of sprites for the background. So it wasn't, they weren't actually achieving the effect the same way that we tackled it. So a couple of the theories that I had initially were just to texture a 3D sphere. I'm using something like WebGL, and then just showing the top half of that sphere. And I kind of like that idea, but I also thought maybe there was a more practical way of achieving the same effect or a similar effect. And I kind of thought, like, what would they have done in the Sega Genesis days if they weren't going to use a sprite sheet, right? Like, how would they have achieved a similar effect? So I decided on this chunking algorithm instead, and basically what that does is it'll take the top about third of our viewport, and it will take chunks of equal size all the way up from a third of the way down all the way up to the top, and then as we get closer to the top, it shrinks those chunks down more and more and more, and then eventually you get that rolling effect. So now that we have a way to create our levels, we have a way to get our infinity grids, and we have a way to get that signature horizon effect, the rest is just basic game programming, and we took it from there. We added our character, added a jump mechanic, a turn mechanic with some rotation math, and we were able to output our final game. Now we have to hop into the AI and figure out how we're going to beat this thing. Alright, so now that we've created the game from scratch, we're going to build the AI that can defeat it. So we're going to utilize a neural network to do that, and specifically we're going to use what is known as a NEAT algorithm, and that stands for Neural Evolution of Augmenting Topologies. Don't worry too much about what that means, but basically we're going to simulate real-life evolution through our neural network, and we're going to do that first and foremost by applying different weights. So let's first go over what our weights are. You'll see that we used 5 in this project. The first of these 5 weights is called blue count, and what that means is at any given moment how many blues are ahead of our player in the current path. Then we have the yellow count, similar. Then we have the distance to a blue, so in our current spot how far away is a blue to us. Same for the yellow distance. And then we have the repeat weight, which is how many moves in a row have we done that are repeat moves, and this does not count going forward or jumping. This is only repeat turns. So as you'll see later in the video, this becomes important because we want to punish our AI for continuously spinning. We want them to be going and making moves. So now that we've got the weights out of the way, we are going to create our population, and on the left you'll see we have these different genomes that we're going to create. So all a genome is a collection of these different weights, and we are going to, for our first generation, we're going to randomly set these weights to a value between 0 and 1. We don't care what they are, the AI doesn't care what they are, we just want to set them across the board completely random. So when we play through the game with our AI, for every move they're going to decide the best possible path forward, and they're going to utilize these weights to do that. So you can see a genome like genome 1 here on the left. It heavily favors the blue count and the distance to a blue, so it might make a decision at a certain junction that favors going towards a blue space. And conversely, if you look at a genome such as genome 4, it's pretty low on the blue count and the blue distance, but it's pretty high on the yellow count and yellow distance. So instead of turning towards a blue, it might continue straight towards a yellow. And that is how the weights go into the decision-making process. So now that we've initialized the population, we're going to go ahead and jump into playing through these genomes. So for each of the genomes in our generation, they are going to go through an entire game. When a genome gets to a possible move, there are only 4 options for it. It can do absolutely nothing and continue straight. It can go left, it can go right, or it can continue straight and also jump. And that's useful if there is a red in front of you, because if you hit a red, the game is over. So the AI is not told what the best move is. At each junction, it uses the weights from this genome to decide what the best possible move is, and then it makes that move. Now, if they use up their maximum moves of 1000, or they run into a red and the game is over, they will end up inevitably having a low fitness and they won't be in the next generation. There are a number of attributes that go into the decision-making process. How many blues are in front of you, how many yellows are in front of you on your current path, is the game over, did you win or lose, is it a repeat move, how close to a blue are you and how close to a yellow are you. And based on your weights and the results of these questions, it decides what the next best move is, or whether your game is over. So now that the genomes have all played through for that generation, we then evaluate the fitness of their performance. So the fitness is calculated based on the entire completed game for each genome. And all that goes into that is how many blues are left, how many yellows are left, and how many moves did it take to get to the end of your game. Initially there is a 1000 move limit, and that is just so that we're not waiting forever for each genome to finish playing. And beyond that, the fitness goes up more. If you get all of the blues, it goes up for each ring that you collect, and the more moves you take, the lower your fitness ends up going. Each genome is assigned a fitness value, and we move into the breeding. So when we breed, the top 50% of the current generation are used as parents for the next generation. So in this example, genomes 3, 4, and 6 are the fittest, and they will be used as the parents for the next generation. So when we go to make a new child for the next generation, the mom and dad are chosen randomly from the top 50% of the previous generation. And then when we go to set the weights for this new child, it's another coin flip between which of the parents we take the current weight from, the mom or the dad. And then on top of that, because if you've been following along, you might realize that if we do this, the generations will eventually end up all being the same. So you have to add in the possibility of mutation. So when you're assigning these new weights from either the mom or the dad, based on that coin flip, you also add in the possibility of a small mutation. Let's say every 5% of the time, when you're assigning a new weight to a child, there is the possibility that we will change that weight by a random value. And this gives you a little bit of diversity in your new genome and allows for new traits to appear and better gameplay to come out of it. So the new generation ends up being the exact same size as the previous generation, and all of these spots are new children made from the top 50% of the previous generation, except for one spot. The first spot in the generation is always the fittest genome from the previous. The reason that we do this is so that it ensures that your fittest from any generation is not a step back from the previous, because you are always guaranteeing that at least the fittest from the previous generation still exists in your new generation. And that way you're always moving forward as you evolve. And then once you've bred a new generation, you simply rinse and repeat, and you're all the way back to playing with that new generation. And eventually, if you repeat this process enough, you will end up with a very well-trained AI. Alright, for the training process for our neural network, we're going to use this very small level with no repeating patterns or anything, and a nice little sampling of what the game has to offer. And this will help the AI learn how to navigate any random field of objects within the game. So let's jump right into it. We're going to set it to step through mode so we can see how it plays along the way. Going to kill our drawing loop so that we can actually train a little bit quicker without drawing to the screen. And we'll build our population. Alright, so generation 0 has finished. You'll see at the bottom here all of the genomes that took the full 1000 maximum moves. So they took a little bit longer to return. And towards the top, you'll have all of the ones that took less than the maximum amount of turns, right through here. And you'll notice that the fittest of the bunch is this 87 move genome, genome 189. And then if you look here, it's pretty interesting. You'll have two that both took 102 moves. The fitness is pretty different between them. One of them is -2, the other one's 14. And what that indicates with the same amount of moves is that one picked up more rings than the other. But let's go ahead and grab our fittest from the first generation and just show you what that playthrough looks like. It is a fitness of 29, but it is an 87 move genome. So we're gonna fast forward through it, through most of it, because it's not very fun to watch at this level. But just to show you what the very early stages of the evolution process looks like. Okay, so that is what the very first generation of gameplay looks like. You may have noticed the wildly spinning out of control. That's something that will evolve out as time goes on, because the more repeated moves in a row, the lower your fitness will be, or the more moves you make across the entire playthrough, the lower your fitness will be. You also may have noticed on a couple of occasions that he actually jumped over rings rather than collect them. And that will also evolve out, because the more rings you collect, the higher your fitness will grow. So let's hop into the evolution process and see if we can't beat that fitness of 29.6. Okay, so just a few generations later, we had a pretty significant jump all the way up to 46 fitness. This is a 54 move genome, so we will fast forward just a bit through it, but let's show you what that looks like. Okay, so we didn't get any rings this time around, but we did cut down on the repeat moves. We started to go in straighter lines for longer distances, so we're moving in a good direction here. Let's keep it going. Okay, we had a slight bump up to 57.6 in our fitness, but we also increased in moves, I believe. We're up to 59. We will fast forward through this one as well. Alright, I think the main difference here is that we ended up grabbing a ring, so that brought our fitness up a little bit. But unfortunately, we're still taking a lot of moves, we're doing a lot of spinning, so we have a long way to go with our evolution. Alright, we have bumped all the way up to 79.3 in our fitness. We're still in the 50s for our total moves on the genome, so unfortunately we're going to have to keep fast forwarding, but we are getting closer to where we want to be. Alright, that was a much improved run. In fact, if you're watching the early portions, you may have even been fooled into thinking that I was a human playing. The later stages got a little bit iffy, but we are definitely on the right track here. So let's keep evolving. Alright, we've had another jump from 79 up to 103 in our fitness. We're at 47 moves, which is pretty good. And let's run through what this one looks like. Right away you'll notice that it's much more decisive on straight paths. It's not doing any spinning of any kind. It does seem to favor longer paths between a blue and a ring. We could definitely cut down on the total moves, but it's much more human-like. I think we're getting to a very good place. Alright, so we are up to generation 24, which is the 25th generation, and we've had another significant jump all the way up to 118 for our fitness, and we are down, as you can see here, to just 32 moves. So I have a feeling this is going to look pretty good. So that's a pretty good place to end it with this small test level. You could definitely continue to evolve. There were a couple of areas where maybe it didn't take the optimal path, but it was fairly close to the optimal path with the information that we've given it. I wanted to close the video by talking very briefly about whether this was all worth it or not. Is this a good way to come up with an AI to beat your simple game like the one that we've created here? And the short answer to that is absolutely not. If you think about what it would take to create a formidable AI for this game and hard code that logic, it would take about 1/20th of the time that it took to build out this AI library, where we decided what the weights should be, what is important, how it can decide and apply those weights to every single move, how to simulate through the entire game for each genome, and evolve together to create a good generation that can play through a level of the game. It's a lot faster to simply write out and hard code the AI for a situation as simple as this. But as a practical exercise, it's worth doing and it's worth learning about because you can apply it to much more complex problems. So thanks for sitting through all of this, and I hope to see you back next time as we build it and then beat it.